Hello, good evening. It's really wonderful to see everyone here. Today we have, of course, a special guest because he's one of us, a new faculty member in the department. So welcome to the 6th Mandel Lecture. My name is Enrico Ramirez Ruiz. I'm the chair of the Department of Astronomy and Astrophysics. We sponsor this lecture in conjunction with the University of California Observatories. And something that makes our Department of Astronomy extremely unique compared to any other department in the UC system is that we host the University of California Observatories here, headquarters, and therefore our partnership has been going on since the inception of the campus. This is, of course, the opportunity that we have to give back to this wonderful community that we have here in Santa Cruz, that we always feel embraced by. And this is a little bit of an opportunity for me to give you a little taste of the sort of research that we do very briefly. And of course, you're going to see a magnificent talk by one of our colleagues. So I looked at the most tweeted story of our department. And so this is basically an incredible experiment. So Saturn basically has these breeding modes, these oscillations, and those oscillations are basically carried through the rings. So by actually seeing the rings vibrate, you can infer properties about the interior structure of Saturn, but you can also infer its rotation rate. So this was work done by our wonderful Chris Mankiewicz, which is a grad student, and his advisor, Jonathan Fortney. And it's kind of surprising when you think about rocky planets like the Earth, if you want to measure the rotational period, you focus in Mexico, which I'm originally from Mexico, and then you look at one cycle around, and then you measure basically how long a day is. But in a gaseous planet, actually, that's very, very difficult to do. And in fact, both Chris and Jonathan did this using basically these oscillations in Saturn and basically said that a day in Saturn is 10 hours, 33 minutes, and 38 seconds. And of course, a year is 29 years. So you can sort of think about living there. And it's an unbelievable work, and it just sort of highlights the creativity that our grad students have here at UC Santa Cruz. I also want to take this opportunity to advertise a new book from one of our wonderful colleagues, Anthony Aguirre. It's called Cosmological Cones. I can, if you look actually at the reviews, it says that the life of readers raised on books like Gödel, Escher, and Bach, and the Dancing Woolly Masters. And Gödel, Escher, and Bach was actually one of my favorite books. It's intense, and I started reading his book, but it's beautifully written, and I really recommend. So Anthony's here in the audience, and we have done a little experiment. So next, on your right-hand side, if you're sitting, there's going to be an envelope. And if you happen to be lucky enough to get that envelope, you will get a copy of the book. And then I want you to come at the end of the lecture here, and Anthony will basically dedicate the book specifically to you. So anyone is the lucky winner. You can, on the right-hand side, it's taped. It's an envelope that is taped. One over there. There's more than one. Maybe we hidden it quite well. Another one over there, yeah, wonderful. And there should be one in the middle section. So just make sure that you put your right hand and find the envelope. Okay, thank you, Anthony. I don't know where Anthony is. Anthony, thank you. His book is available at the bookstore. So yeah, it's a real treat. The other thing that we do here is to give us the opportunity to really thank our wonderful sponsors, Steve and Carol. They've been doing this. This is the 6th Mandel Lecture, and they have just become, part of our family. They are deeply embedded into the culture of our department. Steve trains our grad students about how to give talks and how to talk to audiences, so I'm going to get a written evaluation after this. And he's just been, incredibly generous, and I think, for him it was very important for us to connect with the Santa Cruz community, and as you know, they have done so much for this community. It also gives me the opportunity to highlight some of their beautiful photographs. And I thought this was an incredibly beautiful photograph, and of course very apropos of the topic that we're going to talk today. And he named it A Healthy Coral Reef System, and as a little planet photo, and it's just gorgeous. And just to give you a feeling of who Steve is, I just took the liberty of put his Facebook post. So you actually see how committed he is to everything that should be important to us. And it says it's Earth Day, and these days I'm thinking a lot about the oceans and our suicidal destruction of the planet. Is our species bent on self-destruction? It certainly seems that way. That is one of the reasons why I started Oceans 360. So if you haven't, please check it out. Ocean 360 is amazing. Take some action, no matter how small. Eliminate some plastic thing from your life. Pick up trash on a beach. Contribute money to a conservation nonprofit. Protest. Vote for a candidate who wants to fight global warming. Use your talent or skill for Earth's health. Do anything at all that will help fix Mother Earth. Just do one thing, more if you want. If we all do that, change happens. So I really want to thank and in addition, they're just an incredibly beautiful family, and I'm so glad to call them our family, and thank you so much for everything that you've done for us. So when thinking about Natalie, I thought about this quote, which to me has been kind of seminal in the way that I see the world, and it's just unbelievable. It says, "The time will come when diligent research over long periods of time will bring to light things which now lie hidden. A single lifetime, even though entirely devoted to the sky, would not be enough for the investigation of such a vast subject. And so this knowledge will be unfolded only through long successive ages. There will come a time when our descendants will be amazed that we did not know things that are so plain to them. Many discoveries are reserved for ages still to come, when memory of us will be effaced. Our universe is a sorry little affair, only it has in it something for every age to investigate." So this was 2,000 years ago, and it's incredibly profound. And I think of Natalie as an individual in humanity that has really contributed to change our perception, not only of the world, but of the universe. And here basically shows a chart of exoplanets. These are planets that are not in our solar system, discovered through the years. And you see two very, very important spikes, which are the Kepler planets, which we're going to hear about. And Natalie was basically intimately linked to their discovery. So she's a planet discoverer. And she basically has contributed to radically change our view about life in other stars and life in the galaxy. So a little bit about Natalie. She was Times Magazine, 100 most influential people in the world. She was recently elected to the American Academy of Arts and Science. She's really a UC, a California, public education product. She did her undergraduate at UC Berkeley. We were extremely lucky to have her being at UC Santa Cruz, where she did her PhD. She went to Rio de Janeiro, where she did a postdoctoral fellowship, and then was at NASA Ames as a researcher, where she was basically a seminal component of the Kepler mission. And her footprint in science has been just immense. And I thought, but that really doesn't describe Natalie, all the accolades that come with this. So I also thought about another quote. And it says, "What is important is not the lucky break, the stopping of the train, that's only part of it. Life is full of trains that stop. What counts is what we're doing with our lives when there is no opportunity and no train in sight." So of course, she got the lucky break. She was at the right time, at the right place, and had amazing leadership to lead this team. but she's just an incredible human being. And everything that she does it with purpose, with heart, with kindness, and extreme brilliance. And I thought, when I was trying to describe her, I said, well, this is one of the few instances which I can use her own words to sort of introduce it to you. So I just saw there's a beautiful podcast which is called Becoming Wise, and it's called A Planetary Sense of Love, which I recommend that you hear. It's a beautiful 5-minute podcast, and it says, when you study science, you step out of planet Earth, you look back down at this blue sphere, and you see a world with no borders. You see a tiny mote of dust suspended in a sunbeam. You see the expanse of the cosmos, and you realize how small we are and how connected we are, and that we're all the same, and that what's good for you has to be good for me. And you can immediately see the connections between Steve and Natalie. We were extremely fortunate to be able to attract Natalie to campus last year. She came through a search where the competition was for the entire campus, and we were looking for the next generation leaders and thinkers that can revitalize the university, and we were so pleased that she decided to come. And Natalie, welcome.
I'm overwhelmed by that introduction. That was really nice. That was an overwhelming introduction. I feel a little emotional, so apologies if I'm here getting myself together. Thank you, Enrico. This is a beautiful audience. Clearly, Santa Cruz needs more astronomy in their lives. Yeah. This is amazing. Standing room only. Fantastic. Thank you so much for coming out. I want to thank Enrico, who was the one, I think, who called me and asked me if I'd be interested in coming to Santa Cruz. Maybe he doesn't know that just a couple weeks before I got that call, my own husband said, Natalie, well, is there anybody that could attract you away from NASA, which was, of course, my childhood dream, to work at NASA? And I looked at him and I said, well, actually, really only Santa Cruz. So it was very fortuitous and meant to be. So thank you to Enrico, the department, and Dean Koch for bringing me here to UCSC, bringing me back to UCSC, which feels like home. And then, of course, thank you to Stephen Carroll, Mandel, for bringing me here in this theater, so that I could talk to you about something I'm very passionate about. My work, my love, my science, these amazing results, this amazing discovery. I didn't realize that was still behind me, sorry. Wow, okay. The title of my talk, Lava Worlds to Living Worlds, how NASA mission sparked the search for life beyond the solar system. So lava worlds is a dream realized. We have discovered lava worlds, which you'll hear a little bit about later. And living worlds is a dream to be. It is the part that I think has been catalyzed by the results of the Kepler mission, and that's what I'm aiming to convince you of, or to communicate to you. I hope that by listening to and hearing about the results of the Kepler mission, you will gain an appreciation for that. So this is what we're talking about today, this amazing space telescope that was launched in 2009, a space telescope orbiting the sun called Kepler, NASA's first mission capable of detecting potentially habitable Earth-sized planets. But before I can dive into this, I have to remind myself and you of our humble origins. Before there was this amazing space telescope, there was a lens that belonged to a sports photographer that was being sold on eBay that we bought for a very small amount of money and machined into a tiny case. We borrowed a very leaky, rusty, old, unoccupied, mouse-infested dome up at Lick Observatory that wasn't being used. And the great thing about the Crocker Dome, which you see there on the right, is that there is a straight line of sight right down to the airfield at NASA Ames Research Center, where I worked for 19 years. And that meant that we could use receivers, transmitters to send data back and forth. And so We built this thing on a shoestring budget. The project was called Vulcan, and everything was a kludge. We used sail pulleys to rig up an aluminum shield to protect the camera from rain because the dome leaked. We had a very sophisticated flat field calibration lamp that was made out of an Orchard Supply Hardware paint bucket, Teflon, which is an amazing disperser of light. I had nights when I had to bundle up my infant daughter and drive up to the observatory because the slit got wedged into snow. I didn't realize as I was operating it remotely that there was snow on top of the dome. The weather station said the sky was beautiful. That's because all of the humidity had already precipitated out, and it was right on top of the dome. So this was a labor of love as well. And we worked really, really hard on this project, and we took many terabytes of data. And after about 7 years working on this, all we had to show for it was a mouse named Spock. This is Spock on the toolbox. Yeah, we found nothing. And this is the way NASA missions are born, by finding nothing repeatedly. Over and over again. The Kepler mission was proposed to NASA 4 times and rejected, every 2 years, starting in 1998. When Bill Borucki at NASA Ames, who was the innovator that came up with the technology, when he would walk down the hallways, managers would turn and walk the other way because they knew he was going to ask for money. And we're not talking about a lot, but that's the way it was. I remember when I was at Berkeley as an undergrad, there was a professor there that was actually at San Francisco State at the time, and he was looking for planets orbiting other stars, and everybody laughed at him. They thought it wouldn't happen. And he's now credited as being one of the first discoverers of exoplanets. So I need to say this right up front because that's how great things get done. Number one takeaway from this talk, nothing worthwhile is ever easy. And persistence is key. And the image I chose to represent this takeaway, these little ants working together, is poignant for me because working on a mission like this is about people. I say that finding planets is hard, but the people are harder. And getting a lot of innovative people together that all have very different perspectives, that's amazing. That's what leads to innovation. Getting them to work together is very challenging, but extremely rewarding. Okay. Now, so you want to find life beyond the solar system. I do too. How do you do that? There are basically 3 pathways for finding evidence of life beyond the solar system. The search for technosignatures 1, solar system exploration 2, and then these things called exoplanets, which I will talk about. When you think of finding evidence of life beyond Earth, you might have this image in your mind, right? SETI searches. Search for extraterrestrial intelligence, made infamous by Carl Sagan's book Contact, which was published in 1985, and the movie came out in 1997. Jodie Foster portraying the scientist who was listening for radio signals. The real Jodie Foster actually worked with Carl Sagan, and in 1984, so before Contact came out, she and Carl Sagan founded the SETI Institute, and so the movie is based on the life of this incredible woman, Jill Tarter. And so the idea of technosignatures back then, and to some extent today as well, is to listen to the universe, not with your ears necessarily, but to collect signals from the universe, electromagnetic radiation, and to analyze those signals and look for signals that have an extreme amount of information content that's highly regular and patterned so that it cannot be explained by any normal astrophysical phenomenon, at least that we know about. This SETI acronym has now been broadened in a very formal way. Last year, Congress tried to earmark $10 million for what they called the search for technosignatures. So this is removing this kind of loaded word, intelligence, from the acronym, and now calling it Technosignatures to be more broad. I think that SETI, maybe because of the movie, has been highly connected to this idea of radio searches, really listening to see if some other planet, someplace else, some species on another planet also came up with I Love Lucy, and listening to their radio and television transmissions. But really the search has grown tremendously and now includes a lot of really interesting work, like Shelley Wright's work at UC San Diego, depicted in the bottom left, coming up with a wide field all-sky camera and very sensitive infrared detectors that can measure signals on very tiny microsecond timescales in order to search for high energy pulses, basically lasers. The idea that maybe other civilizations are using lasers for communications in the same way that we do. It's also looking at any kind of astrophysical data and looking for anomalies. And one of these happened, maybe you're familiar with Tabby's star. This was a star that was observed by the Kepler spacecraft itself and showed a pattern of signals that didn't look like anything that we could pin down as being astrophysical. And it perplexed scientists for many years, and it took a long time to sort out. And so on the bottom right-hand corner, this is our sci-fi representation of maybe what one of these technologies looks like. It's a structure that has been built enveloping an entire star in order to harness energy, because that's what life does. That's what complexity as it arises in the universe does. We harness energy to do work and to fight against the laws of thermodynamics. And so we look for interesting ways that other civilizations might be trying to harvest energy. So that's technosignatures. The second pathway, of course, is the solar system. And you're saying to me, well, wait a second, the solar system is a big dead place. There's nothing else living out in the solar system, right? I mean, we've seen these images of Mars that are, by the way, so amazing. It feels like you can actually hear the dirt crunching underneath your boot. They're so fantastically real. But what you don't realize is that Mars, yes, it was once a wet place with surface liquid water flowing, as you can clearly discern from these mud flat-like structures here. But even today on Mars, there is frozen water. Here is frozen water in the basin of an impact crater that is shielded from the heat of the sun. There is a lot of frozen water on Mars. And so the idea is that, well, okay, maybe there used to be life on Mars. Maybe now there's only death in the form of fossils. But it's also possible that if we go down maybe in a subterranean or subsurface cave someplace where the temperatures are warmer, maybe some of that water that's locked up into the geological layers could actually melt and do some interesting chemistry. And the only way we're going to find that out is if we send maybe robots, but also humans there to do some digging. But Mars isn't the only place that's interesting in the solar system. We now know that there is liquid water in the sub-ice layers on the moons of Jupiter and Saturn. And we know this in part, or primarily, due to these incredible images that were taken by the Cassini spacecraft. As it was orbiting Mars, it did some flybys of satellites of of Cassini. Did I say Mars? Of Saturn, sorry. Did some flybys of some of the satellites of Saturn, including this icy moon Enceladus. And it caught an image of Enceladus as it was being backlit by the sun over a region where we knew the surface showed evidence of heat and cracks, fissures that were hot. And sure enough, emanating from those cracks, being backlit by the sun, are these geysers that are emanating from below, showing evidence of liquid water underneath the ice. And so where that liquid water interfaces with rock, you have all of the complexity, all of the atoms, the complex atoms that you need for organic chemistry, and maybe even some energy due to tidal heating underneath. Then that's probably what is melting the ice as well. Enceladus isn't the only place that shows these geysers. Jupiter's moon Europa also shows these geysers and is a very, very interesting place that NASA wants to go to next. And I think one of the reasons NASA wants to go there is because it turns out, fun fact number 2, there's more liquid water on Jupiter's moon Europa, under that ice, more water there than there is on Earth. Tremendous amount of water. Interesting chemistry could be going on there. And so who knows? The takeaway message here is that, yes, we look around in the solar system and we don't see anything living. That is, life hasn't taken a global toehold on any of the other planets or moons, at least that we can see. But it could exist in niches, and we need to explore the solar system to find out. Okay, the third pathway towards finding life beyond the solar system opened up in the 1990s, and I was actually a graduate student here at UC Santa Cruz at the time. My advisor was Steve Vogt, who built an instrument that was being commissioned on the brand new Keck 10-meter telescope. And because I was his student, I had the opportunity to work with some of what's called the commissioning data. It's like the test data, the first engineering data. And it was something everybody in the world wanted to see, because this was data unlike anything that anybody had ever seen before. And he got invited to a conference in Florence, but he couldn't go. And I was a young mother at the time as well, and I wasn't attending conferences. But hey, Florence, that was like a great opportunity, not just for me, but I could actually convince my mom and dad to go too, so that I could take my young toddler with us, take him in tow, and I did go to this conference. And the reason I'm bringing it up is because on the very last day of that conference, on Friday, not on the agenda, not on the program at all, not even in the description of the abstract of the speaker, all of a sudden Michel Mayor, this Swiss astronomer, gets up on Friday afternoon as most people are leaving and announces the discovery of the very first planet orbiting another sun-like star in our galaxy. The host star was called 51 Peg. Peg is the abbreviation for Pegasus, the constellation Pegasus. And so I'm going to come back to that, but first let's just establish this. Planets beyond the solar system, so we're not talking about planets in our own solar system. Planets orbiting other stars in the galaxy are called exoplanets, or sometimes you'll hear them called extrasolar planets. Both of those prefixes meaning outside of the solar system. Okay, so this is an artist's rendering of this planet, because the methodologies that we use to find planets aren't like what you see in the cartoons. We're not taking gigantic telescopes and looking around the sky and saying, aha, there's one. Everything that we discover, not everything, but most everything we discover is through indirect methods. We are learning something about the star itself that is inferring the existence of the planet, and that was no exception for this discovery. So we don't have an image like this. What we do have is a set of measurements that tell us about the size of the planet, its radius, its mass, its orbital period, and through Kepler's laws of planetary motion, the distance between the planet and the star that tells us how hot or cold it is. We can build a picture in our mind grounded in physical models to really get an image, build up an image of what the planet is like. And we give all of that information to the artists, and they make them come alive. And that's what you're seeing here in 51 Peg. 51 Peg little b is the planet itself. It's a Jupiter-sized planet orbiting about 8 times closer to its sun than Mercury is to our own sun. So it is unlike anything we have in our own solar system. All right. Now, let me say a little bit about the detection technique. It's called the Doppler method. Clap if you've heard this. Okay, great. So this is not for you. Everybody else, you know that planets orbit their stars, correct? But what you might not know is that stars also orbit their planets. And in fact, what's going on, as you can see from this animation, is that these two objects are orbiting about their common center of mass. So if you could imagine the star and the planet being connected by a rod, and you had to place your finger on a fulcrum to balance them, your finger is going to be placed very close to the star because it's heavier, right? That's the point about which the planet and the star orbit. So the planet is accelerating a lot because it's so far away from that point. The central star is wobbling, we say, just a tiny bit. All right? Now, that's great. So what we want to do is we want to detect evidence of this wobble. And again, it's very difficult to point a telescope and actually see it wobbling because the center of mass, this is quite exaggerated, the center of mass is actually inside the radius of the star. So the wobble is very slight. Okay? So instead, what we want to do is we want to collect the light from the star and we want to spread it out into a gigantic rainbow. You've seen starlight, sunlight filtering through a prism, a crystal maybe, in your home or in the car, and it projects a rainbow onto the wall. Here's a rainbow of our sun. This rainbow that's being projected is so wide, it can't fit on one detector. We actually have to chop it up and stack it. So you've got red, orange, yellow, green, blue going from top to bottom. Beautiful rainbow of our sun. But if you look carefully, what you notice is that superimposed on this rainbow, there are colors that are missing. Those are colors that are being absorbed by elements in the atmosphere of the star. They never make it to our telescope or to your prism hanging or your crystal hanging in the window. Okay, let's see, and some of them are, this pattern of lines that you see here is really a chemical fingerprint of those elements. For example, the two dark ones in the yellow are due to sodium. The dark one up in the red is due to hydrogen. In the green, we've got a magnesium triplet. So these elements eat away very specific colors, creating this chemical fingerprint that allows us to discern not only what the atmosphere is made out of, but also what its temperature, pressure, structure is, its density. Okay, now, if a star is moving or wobbling, now we're going to, I'm going to play an animation. We're going to zoom in on one of these lines in the yellow. Let's say that one. We're going to look at it. That absence of color is moving back and forth, and this is the Doppler effect. And the grid that you see on the background are the light meters that are measuring how much light is being emitted at every color with very fine detail. And you can see the detectors are going up and down in response to the motion, right? So a star emitting light is analogous to, let's say, a boat moving through water, creating a wake. The waves are bunching up in the front and spreading out in the back, and that's what you're seeing here. These changes in colors back and forth are waves bunching up and spreading out as the star moves towards you and away from you. That's the Doppler effect. So we're utilizing this Doppler effect to back out or to compute what the motion of the star is, and that's how 51 Peg B was discovered. And in fact, the motion of the star for 51 Peg B, that speed, orbital speed, is about equivalent to a car driving down the freeway. That's what we were measuring. Okay? All right, and that first planet looked nothing like what we have in our own solar system. You probably all learned in school. The small rocky things are close to the star, the big ice and gas giants are far away, right? And here, the very first planet we discover is a giant planet 8 times closer to the star than Mercury is to our own sun. So it completely upended our understanding of planetary physics and how architectures of planetary systems are put together. It also is the first thing that gave us this notion that maybe our solar system is not completely typical. We don't know. So all of these questions opened up, and it really motivated us to push the envelope further to try and find even smaller planets and planets more like Earth. And in fact, what we wanted was something just like home. What we wanted, now it was within our reach. We could feel it. It was within our reach to find the true Goldilocks planet, right? The planet that's just right for life as we know it, right? Okay, but what does that mean? What is the just right planet? Well, really, we can only measure size, mass, orbital period, how hot or cold the planet is. So we have to think in terms of those quantities. And when you're thinking about life, what you want to do is you want to look around on planet Earth at all the species of life on planet Earth. You want to go to remote areas. You want to go where it's very hot, where it's very cold, where it's very saline, where it's very acidic. You want to go where there's no light at all. And you want to ask yourself, is there life? And everywhere where we go on planet Earth, no matter how strange, there is life. And some of that life does not require oxygen. Some of that life does not even require sunlight. But there's one thing that all forms of life have in common on planet Earth. One thing that life has in common is that it's all carbon-based. And there are physical reasons for that, most likely, because carbon is very special in the way the electrons are organized around the element and how they can form complex chains of molecules. It's very special. And for organic chemistry, as it operates on planet Earth, the solvent that facilitates all of those chemical reactions, like metabolism, cell transport, bringing in nutrients, taking out waste, all of those processes are facilitated by water. And liquid water also has very special properties. So we're looking for water, and that means we're looking for planets that aren't so hot that all the water is in vapor form, and not so cold that all the water is frozen in a locked up in a frozen state. And we can make these calculations. We can take an Earth, and with our climate models and our Earth structure models, we can say, what happens to this Earth if I move it closer to the star? What happens to this Earth if I move it further away from the star? And we can begin to understand the limits of planetary habitability, the limits where liquid water could not pool on the surface of a planet. And it turns out that that range is relatively narrow. A third of the energy that the Earth receives, up to maybe 170%, that's basically the orbits of Venus to Mars. And in our own solar system, how many planets do we have between those two? One. Just one. Okay? Now, okay, so Goldilocks in terms of the orbits. Goldilocks also is looking for the just right size. And this might be as well, probably not a human bias, but it is model-based to some degree. In our own solar system, we believe that all of the planets have rocky cores, and all of those rocky cores are about the same size, more or less. And it just goes back to how many heavy elements are in the giant molecular cloud from which that star formed. There's just only a certain amount of materials available. Right? So all these rocky cores are about the same size, but then what does that mean? Why is it that we have giant planets versus tiny terrestrial planets and asteroids and comets? And the answer lies in what other elements are available. And in our solar system, or in any giant molecular cloud, it's predominantly hydrogen and helium. So when you get far away from a star, you are able to also accrete on the hydrogen and hydrogen molecules that condense out. And that process builds up the ice and gas giants that are far away. And the implication is that if you want to build a giant planet and put it 8 times closer than Mercury is to our sun, you're going to have to do it far away first and then bring it in through dynamics, through gravitational interactions. Okay, so we want to find planets where the base materials that our bodies are made out of exist, right? That's the CHNOPS thing. Carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur. Did I get that right? I'm not a biologist. CHNOPS. And interestingly, all of those things, most all of those things, are the predominant elements that are manufactured in the cores of stars. So that's probably not a coincidence either. So you're not looking for hydrogen and helium because you can't build complex chains out of just hydrogen and helium. You're not going to be able to build up complexity, although it's important. you need the stuff that rocks are made out of. So we're looking for rocky planets, and those are not the ice and gas giants. And the ice and gas giants, by the time you get down to the rocky surface, the temperature, or the pressures there, and the temperatures too, are, you're talking millions of bars of pressure. You're talking tens of thousands of degrees Kelvin. DNA cannot remain cohesive at those temperatures and pressures. Okay, so that's 51 Peg B. I want to pause here for a second and say, okay, well, we're looking for Goldilocks planets. Now let's just use the Doppler method and find tinier speeds, tinier wobbles due to smaller planets like Earth. And I say, well, yes, that's great, but the wobble of a star due to a planet like Earth at its orbital period, that's going to cause an orbital speed or wobble of the star that's not a car hurtling down the freeway. It's more like a ladybug crawling across the stage. It's centimeters per second. It's very tiny, okay? We don't have, I think they put like pheromones or something in the ink. I don't know why the ladybug is following the pen. We don't have the technology with the Doppler method yet to measure such small speeds, such small wobbles of a star, all right? We needed a new technique. And that's where Kepler enters. Ta-da, we're at Kepler. Bill Borucki, I mentioned his name before. He's the innovator and the man who got Kepler funded and got the technology built. Kepler is a space telescope orbiting the sun. Its mirror is about 1 meter across. And Kepler's job was to use a method called transit photometry. Kepler had one job, and that was to look at one patch of sky about the size of my hand, observe tens of thousands of stars. In fact, it observed about 200,000 stars simultaneously. All it had to do was measure the brightnesses of those stars with very high precision. So the idea is based on eclipses. The idea is that if stars and their planetary systems are all oriented randomly in the galaxy, some of those planetary systems will be orbiting such that the planet passes directly between the disk of the star and your telescope. That planet is going to cast a shadow out into the galaxy, and that shadow, under certain alignment conditions, is going to sweep across the face of your telescope. Your telescope will perceive that as a momentary dimming of light, as you see here on the green trace below. So you're measuring brightness. The brightness decreases. How much the brightness decreases tells you the size of the planet. On the left-hand side, you see a black disk the size of Jupiter in front of the sun. Jupiter would take away about 1% of the light. If you could imagine 100 light bulbs, you take away 1. That's the dimming of light that you get from a Jupiter. On the right-hand side, maybe you can't even see the tiny dot that is Earth. It's very small. It's about the size of a sunspot, actually smaller than most sunspots on the sun. And it takes away 1/10,000th of the light. Okay, what does that mean? The analogy I like to use to describe this is to imagine the tallest skyscraper in New York City. Maybe it's 80 stories high. I guess they're probably bigger now. I don't know. I did the calculation for 80 stories. And it's nighttime, and every window is illuminated. And one person in that building goes to the window and lowers the blinds by about 1 centimeter. That's the change in brightness that you have to be able to detect. That means that your detectors have to have precision comparable to parts per million. All right? Okay. So to summarize this, well, let me just back up a second. How much the starlight dims tells us the size of the planet. How frequently it reoccurs once every orbit tells us the length of that planet's year, right? The orbital period. And Johannes Kepler in the 1600s taught us, this is the namesake of the mission, taught us that there's a direct relationship between the orbital period and the distance between the planet and the star. And if we know that, and we know how hot the star is, we know how much energy the planet is receiving, and whether or not it's a Goldilocks planet, right? Okay. So basically, to summarize, NASA's Kepler mission had a 10-year staring contest with the universe. It had to measure brightness, basically without blinking, of about 170,000 or so stars simultaneously in order to catch these dimmings of light that only last for like a few hours. Okay? The ultimate staring contest. Okay. And so it did that for 4 years, staring at the summer triangle in the constellation, or between the constellations of Cygnus the Swan and Lyra. So between Vega and Deneb, kind of tucked under the wing of Cygnus the Swan, in the plane, near the plane of the Milky Way galaxy, where there's large numbers of stars, we stared unblinkingly at Cygnus for 4 years. Then the mission was extended, and we spent another 4 years looking at other fields along the zodiac, or the ecliptic. So an 8-year mission total. Okay, so this is what the data looks like. Have to show some data. A bunch of white points just kind of all over the place, right? You look at the data, every white point represents a brightness measurement for one star as a function of time. You notice there are blinks. There are some places where there are no white points. That's where the spacecraft did blink. It had a safe mode event or something that shut it down momentarily. But for the most part, it observed the same star for 4 years. Here I'm only showing about 200 days, less than 1 year of data. But you might also notice that there is a periodic drop in brightness. And if you're having trouble seeing them, I'll mark them for you. There they are. And this is due to a planet orbiting the star. Again, we're inferring the existence of a planet through indirect means by observing something about the star itself that tells us there is a planet, that belies the existence of the planet. Okay, so now I'm going to zoom in on one of these transit events, we call them, because the planet is transiting in front of the star. Let's look at one of them, let's say this one, and I'm going to zoom into that data, and this is what it looks like. So now you see quite clearly this momentary dimming of light. But if you look carefully, you might convince yourself that there is another sequence of dimmings of light that are periodic on this same star. And you would be right. Here they are. This was really exciting. We saw this signal in the data from the first 10 days of spacecraft operations. And this dimming of light that you see there marked in red is due to a planet that is pretty much the size of Earth. This was our very first rocky planet discovery, Kepler 10b, and I'll talk more about that in a second. Okay, I want to summarize for you the magnitude of Kepler discoveries, and I'm going to do that with a scatter plot. First, I will say, and Enrico already alluded to this, that the number of new planet discoveries has actually been growing exponentially since that first discovery in 1995. And any day now, the number of discoveries is going to hit 4,000. So we know of orders of magnitude more planets outside of our solar system than we do within our solar system. But this is what the scene looked like on the eve of Kepler's launch. I've got the radius of the planet, because we get that from the dimming, how much it dims, and the orbital period, the time it takes for the planet to go around once on the x-axis. And every point that you see here was a planet discovery that was made before Kepler launched. And I have some horizontal lines that show different sizes for reference. And you see here that 85 or even 90% of the discoveries before Kepler launched were larger than Neptune. And I've got points that are colored blue if they were done through this Doppler method, which I'm calling here the radial velocity method. Or pink if they were identified using the same transit method, but from ground-based telescopes. So now I'm going to add to this diagram the Kepler discoveries from that first 4 years. All of these planets come from Cygnus the Swan, that region in the sky called Cygnus. And I'm going to add these points in yellow. I like all those wows. Yes. You put a new piece of technology out into space, a new way of looking at the universe, and suddenly the blinders are lifted. Suddenly, what we couldn't see is now seeable. Now our blinders have been lifted to the population of small planets in the Milky Way galaxy. Now, over 90% of the planets known to humanity outside the solar system are smaller than Neptune. So what we saw before was an observational bias. Now we know that small planets are relatively common. There's a lot of structure in this diagram that I don't have time to get into, but feel free to ask questions about it later. I'm going to make a couple of points. Up until the point of Kepler, planet discoveries were like stamp collecting, right? Every new planet discovery was just like, wow, new planet, what is it? All of a sudden now we're getting planets in the hundreds and the thousands, and that means that we have access to different science questions. This means that we can now do demographics. We can study planets as a population in the galaxy. We can understand how common planets are of different sizes. And one of the things that we learned almost immediately from Kepler is that the diversity of planets in the galaxy far exceeds the diversity of planets in our solar system. We found all kinds of crazy things, and I'm just showing a few of the thumbnails of artists' conceptions of these worlds. And I'm just going to quickly run you through some of them. In the upper left-hand corner, you've got a planet that is glowing yellow on one side. This is Kepler 10b. This is a planet that is not 8 times closer to its star than Mercury is to its sun, but 22 times closer. It has an ocean larger than the Pacific Ocean, but not made of water, made of molten rock. The temperatures on the star-facing side are in excess of that required to melt not just rock, but iron at standard temperature and pressure. Now, if you take that idea and you move it even to more of an extreme, let's say you put the planet even closer, eventually that big ball of rock is going to photodisintegrate. And we see this happening in the Kepler data. So the next thumbnail is not a comet, but a planet, an entire Earth that is being shredded apart, melted and sublimating in front of our eyes, creating this enormous planetary scale size comet-like tail trailing behind it. And we see that because the dimming of light has a different shape. Okay? The next thumbnail is this blue orb. This blue orb represents what we loosely refer to as super Earths, or maybe mini Neptunes, depending on how you think about it. But the idea is that there are planets that have too much of a good thing. Planets that are probably entirely covered in liquid water. So much so that it doesn't give access to the rocky core in order to build up complexity for life. The next thumbnail is showing a planet orbiting not 1, but 2 stars. This is called a circumbinary planet. So you would go out in the morning at sunrise, you would look out in the east, and you would see not 1 sun rising above the eastern horizon, but 2 stars, changing places as they go across the sky in their mutual gravitational orbit. We have planets that are orbiting stars in bound clusters, star clusters, like the Pleiades star cluster, but even more dense. These planets, if you stood on them and you looked up at the night sky, you would see a bejeweled sky, unlike ours, due to the higher density of stars. And then finally, in the upper right, there are planets orbiting dead stars. But perhaps more importantly, there are planets orbiting stars, planets that are the age of the galaxy itself. These planets were born from rocky-like material that was generated from the very first supernova explosions during the formation of the galaxy. And the reason this absolutely blows my mind is because that means that there are rocky planets where life has potentially had not 4 billion years to evolve, but more like 11 billion years to evolve. And it makes me wonder what complexity might do if given 11 billion years to evolve. I mean, we tend to think of ourselves as the pinnacle of complexity in the universe, and that might not be true. There might be other planets that have been evolving complexity for even longer. Okay, the next fun fact is that the bulk of planet discoveries so far are a type we don't even have in our solar system. So to drive this point home, and we're going to look at the data a little bit differently. Instead of the scatter plot with all those dots, we're going to have a bar graph. We're just going to count the planets at different sizes. And I'm going to make it really easy for you. If the planet size is about that of a terrestrial planet, like Mercury, Venus, Earth, and Mars, I'm going to color the bars blue. If the planets are more like the ice and gas giants, like Jupiter, Saturn, Uranus, and Neptune, I'm going to color the bars blue, so brown and blue. And here's what it looks like. Brown on the left, blue on the right. And the takeaway message from this diagram is that the most common type of planet that we know about is literally the gray area in between. It's a type of planet, as you can see on the top, we don't have. And these are those kind of mysterious super-Earths, mini-Neptunes that we don't really understand. So this is going to be an amazing science adventure going forward in the next few decades to really understand the nature of those planets and why we don't have any. Okay, a couple more things to tell you about Kepler before we move on to the future. First, Kepler was a statistical mission. So that means that we can take the discovery space and we can transform it into the intrinsic population of planets out in the galaxy. I can make all of the bias corrections for our observational biases that are inherent in this diagram, and I can correct for them and show what the fraction of stars that have planets of different sizes really is. And that's what this bar graph is telling us. So now on the y-axis, I have the average number of planets per star for different sizes, and this is the intrinsic number of planets out in the galaxy. And if you add up all of those numbers, like 0.4 for the rocky planets, 0.3, 0.35, 0.18, etc., you quickly get to a number greater than 1. That means that the average number of planets per star in the galaxy is greater than 1. On average, every sun-like star has at least one planet because this sample is only sensitive to planets from Earth orbits inward. And that means when you look up at the sky at night, every pinpoint of light that you see is not just a star, it's a planetary system. What about the Goldilocks planets? We've learned about that too. The Goldilocks planets, I can tell you what the average number of planets per star is for Goldilocks worlds. But instead of just quoting that number, we're going to do a thought experiment. We're going to take the Milky Way galaxy and we're going to shrink it. And we're going to shrink it down to the size of the continental United States. And we are here in Santa Cruz standing with our backs to the Pacific, looking out across the continent, which is our galaxy. And we're asking ourselves the question, where is the nearest potentially habitable planet likely to be based on the Kepler discoveries? Out across the continent, where is it? And the answer, it turns out, is like right here at Mackenzie's Chocolates. Yeah, it's very close. If you go in that direction, it's about Whole Foods. Okay, so the nearest potentially habitable planet is expected to be within 10 light years. Well, all good things must come to an end, and Kepler came to an end as well very recently. It came to an end when it ran out of the fuel, the small amount of fuel in its tanks that allow us to spin down the gyroscopes. And so in October of last year, we saw headlines like this: R.I.P. Kepler, so long Kepler, thanks for all the planets. The little spacecraft that could no longer can. It was pretty depressing. As you know, Kepler's namesake was Johannes Kepler, the scientist. You might not know that he wrote his own epitaph. And in part it reads, "I used to measure the heavens, now I measure the shadows of Earth." So I think it would be befitting if Kepler, the spacecraft's epitaph, read, "I used to measure the shadows of Earth's," plural. But what I also find remarkable, and this was a total coincidence, is that the spacecraft was shut down, spacecraft died basically on the same day, the anniversary of Johannes Kepler's own death. How's that for synchronicity? Okay. Number 11, send a poet. It's my takeaway message. It's a reference to Jodie Foster in Contact. There's a famous scene where she says they should have sent a poet. My colleague Doug Caldwell took a screenshot of the operations engineer's log the day that Kepler was turned off. There's a lot of really cool lines in here. Mom, which stands for the Mission Operations Manager, not actually a mom, has given the go to send the good night command. The good night sequence command has started. Flight director is calling it. We believe the good night sequence has made it in. And finally, so long Kepler, thanks for all the fish. So what is all this reference to the good night sequence? I mean, yeah, okay, it's poetic, putting it to sleep, I guess, I don't know. Well, it actually comes from, it's a nod to the movie Interstellar. But in this scene, the engineer recites a Dylan Thomas poem, and in fact, he really immortalized Dylan Thomas through this movie. This poem wasn't as well known before the movie aired. But it's called "Do Not Go Gentle Into That Good Night." Do not go gentle into that good night. Old age should burn and rave at close of day. Rage, rage against the dying of the light. Though wise men at their end know dark is right, because their words have forked no lightning they, do not go gentle into that good night. Do not go gentle into that good night. So that was the nod that the Ball engineers implemented. Thank you. In their good night sequence. And I think Rage Kepler did. It did not go gentle into that good night. This is Kepler by the numbers. By the end of the 8 years, it observed almost over 500,000 stars, discovered 2,600 planets and counting. There are another 2,000 or so candidates that are in the wings still being worked on. It observed 61 supernovae. It observed solar system objects. It revolutionized stellar astrophysics, collected 678 gigabytes of data, not much actually considering given the science. It's traveled 94 million miles and all for 3 gallons of fuel. Pretty good. Yeah. Okay. I think I'm going to skip ahead a little bit because I do want to give you guys time for answering questions. And maybe if you want to ask questions about the future, I can touch upon that in the Q&A. I would like to say a little bit about what it was that attracted me here to UC Santa Cruz. You know, a girl who grew up during the space shuttle era, who met an astronaut as an undergrad at Berkeley, Ray Seddon, dreamed of going to NASA, not a childhood dream necessarily, but a dream that came while I was at UC Berkeley in college. Finally, after a decade or so, achieved that dream, and now here I am at UC Santa Cruz. Why? Well, Kepler and these results, the fact that the nearest habitable planet is there at Mackenzie's Chocolate, tells us that finding evidence of life and being able to look up in the sky and not just see those pinpoints of light as planetary systems, but to be able to point to a star and say that star has a living world. We are not alone. That is profound to me, and it's profound to many people in the government as well. And in 2017, the Congress, through the 2017 Space Authorization Act, they put language into the Space Authorization Act that added a 10th objective to NASA as an agency. Like, what are the 10 big things that NASA does? It used to be 9. Now it's 10. And number 10 is the study of the origin, evolution, and distribution of life in the universe. So, yeah. So I don't think it's an exaggeration to say that Kepler has catalyzed the search for life on exoplanets in a tangible way. We didn't get to talk about it, but we know how to do it. We're going to do this by looking at the colors of planets and measuring the chemical fingerprints of their atmospheres. That's going to tell us if the atmospheres have greenhouse gases, water vapor, and even the metabolic byproducts of life that has taken a global toehold of the world. We know how to find those, what we call biosignatures, like oxygen, the byproduct of photosynthesis. And this endeavor is under the umbrella of what's called astrobiology. The melding of astronomy and biology, the search for life out in the cosmos, but we recognize that that search is multidisciplinary. It encompasses all of these topics that you see here on this slide. We have to understand not only the origin of complexity, but we have to understand what it produces, the kinds of biosignatures that life produces. We want to understand the variety of ocean worlds out there and where life might be able to take a toehold. We want to be able to look back in time at Earth and see what lessons we can learn. How did complexity arise here on planet Earth, and what did it leave behind? Before the great oxygenation, when photosynthesis increased oxygen levels to a very substantive percentage. And we want to look at planets in a system science way. We want to look at coupled models of the geology, the atmospheric science, as well, and the climate, as well as the biology. So biogeochemical models of planets as that comprehensive system. So all of these things need to come together, and what I knew about Santa Cruz is that those things are already happening, because Santa Cruz is already a very interdisciplinary place. We've got astronomers, planetary scientists, earth scientists already working together. We've got amazing expertise in the departments of biology, as well as the biomolecular engineering departments. This is already happening. All they need here at Santa Cruz is a little bit of catalyst to focus the efforts of these people and get them to work together, but really they're already doing it. So I saw that as an amazing opportunity to continue the legacy that was Kepler, and to grow it going forward, to utilize these ground-based telescopes, the Keck and the future TMT that are being built here, to further this endeavor. So I think the takeaway message from that, because we know what to do, we could have the answer to the question that's on the cover of this Nat Geo issue in just a few decades. So that's the science reason why I came here. I also came here for other complex reasons. I think Santa Cruz is a very special place. Equity and inclusion, let's talk just briefly about that. What you're seeing here is a picture taken in 1987. It was my very first summer internship in science. I hadn't even decided to be a science major at this point. In fact, I told my advisor at the beginning, I said, I'm not like these other kids. I'm not going to go into science. I'm not going to get a PhD like they are. Right. Okay, so there's this picture. This picture was, it's from my history. It was in my mind. Me in this like bright pink sweater with this group of interns. Now, fast forward 27 years, my second child got a PhD in astrophysics. And she sent me a picture of her freshman class of grad students at Penn State. And this is what the picture looked like. And keep in mind, this is like 17, 20, no, I can't do math. 13 plus 27, mental math. I can't do mental math. 27 years later, and this is what that picture looked like. And I saw this picture when she sent it to me, and I just thought, for goodness sakes, 27 years has gone by and not much has really changed. Yeah. I also noticed around that time that, one, Santa Cruz was doing amazing things, but also that being a female in science was attracting more females. Not because I was really doing anything, but just besides existing. The students were coming to me for supervision, and I've seen that echoed time and time again. Here at Santa Cruz, many people are working extremely diligently to improve equity and inclusion at UCSC and in astronomy in general. You know, the percentage of females is low, still low to this day, but persons of color, it's even worse. It's unacceptable. And I made a comment at the beginning of this lecture that when you have diverse perspectives together in a room, you maximize innovation. And yes. So I am a huge proponent of this. I had so many programs to choose from, I didn't know where to begin. I'm highlighting the Spanish lecture series that is hosted up at Lick Observatory to bring students from mostly Hispanic serving schools in the Bay Area and its environs to learn about astronomy, but also to look through telescopes, which is a tremendously powerful experience. Also here at Santa Cruz, for the very first time, a presidential chair was named. Our very own Enrico Ramirez Ruiz took on the presidential chair for diversity in astronomy. And I don't know of any other program like that in the country. In Denmark recently, I saw this art. It's a traveling exhibit. The artist, I can't pronounce his name, I'm sorry. It's a Chinese, very prominent Chinese artist. These are floor-to-ceiling maps of technological ethics. He takes a map of a fictitious world and he turns all of the geographical places into ethical statements, giving them names that are ethical statements. And at the bottom, I don't know if you can read it, it says, "Why do we want to escape from Earth?" as one of these ethical questions. And I've been asking myself a lot of ethical questions lately. We're going to Mars, says Elon Musk. Well, I'm not sure that we're very good planetary stewards. Seems like we should be thinking about that. For one, there are numerous ethical conundrums that we are facing today, and in my field as well. And I feel very strongly that we need to step back and think about them. And a couple weeks ago, there was this event at UC Santa Cruz. It was called an Ethics Bowl. It was like a debate, but set up in a different format to discuss the ethics and future of humanity. Basically, the question is, should we really invest resources to model what happens to planets in 1 million years? Or should we solve the immediate problems here on planet Earth? And that's a very complex question. And the faculty were there talking about it. And I was blown away by this. I think that this is extremely important. Okay, so finally, what we learn about the extremes of habitability in the galaxy will help us understand the sustainability of life right here on planet Earth. So it's that quote, you know, the T.S. Eliot quote from Little Gidding, right? That's become almost cliche because we've heard it so many times. But it holds true. We shall not cease from exploration, and the end of all of our exploring will be to arrive right where we started and know the place for the first time, and that holds here true here as well. So I'm going to end there. We have a little bit of time left for questions with this amazing quote that was put into an essay contest sponsored by Kepler in honor of Carl Sagan sometime around 2011 or so. It's my favorite quote that ever emanated out of Kepler science. So I hope you enjoy it. Thank you so much for coming, and I hope that... Thank you. Do not go gently into that good night. Thank Oh my goodness. Thank you. Do we have time for questions?
We have a few minutes for questions, and as customary in the Mandel lecture, we give priority to the children. So any children in the audience that want to ask a question? Yes, I see you.
How would they go about asking a question?
I know. Maybe raise their hands.
Is there a microphone?
There's a microphone here. Will you come? You can raise your hand and I can repeat your question.
I tell you what, if kids ask a question and you give me your address, I'll send you some stickers and pens and fun things. Just bribe them. I have 4 kids. Hi.
You can get close to the mic.
I believe you wanted to study philosophy, right? Before you became an astrophysicist, right?
For like a hot second.
Like a hot second? Well, does anything you've learned in astrophysics, yeah, that word, strengthen or weaken anything you've previously thought about or learned in philosophy?
Oh my God, that is such a good question. Damn.
That's what we do it, go into the core.
Oh my gosh, where do I begin? Okay, she's right. When I was 15 years old, I went downstairs and I told my mom very proudly I decided what I was going to be, and it was going to be a philosopher. I had no idea what that meant. I think I read Jonathan Livingston Seagull or something like that. I don't even know. That was the basis of it. Studying science, we all have these really deep existential questions. Why am I here? What is my purpose? What are we doing? What is our future? Are we evolving towards something good? Or is everything just random? When I was in my first physics class at UC Berkeley, and I took my first physics class late, the professor was describing the refraction of thin films and how oil on the surface of water produces that iridescent color. And he just wrote a simple equation on the board. And my head exploded. I was like, wow, the universe is not chaotic. It can actually be described by numbers. And I thought to myself, what's the limit? What mysteries can be revealed? What mysteries cannot be revealed? Is there a limit to what we can learn? And just the fact that the universe was ordered in that way, that in and of itself gave meaning to my life. Over the years, it has made me love mystery, to almost revere mystery, and to embrace it, and to be comfortable with what I don't know, and kind of trust that everything is exactly as it should be, even when things seem sucky. Very good. You can come up and wait.
Yeah, come on, and we have a line. You can move the microphone a
little. When do you think you're going to find a planet that we could potentially live on?
when are we going to find a planet that we could potentially live on? That's such a hard question, because one thing is to find a planet that might be inhabitable. It's another thing to find a truly habitable environment that already has water and all of those great things. That's hard, but I think that will take us about 20 years, 20 to 30 years. But then the other part of your question is that we could live on. That implies that we go there. And that's going to be more difficult. That's going to be on the timescale of hundreds of years. So maybe like your great-grandchildren. Okay?
Yeah.
Okay.
Right. Oh, okay. So when you see a star and its light kind of dims, how would you discern whether that's from an orbiting planet or something like the star being a variable star?
Yeah, oh, such a good question, these kids. When I was a postdoc, so I had just gotten done with school, and I was studying spots on stars, like sunspots. And the sun spins, so sunspots go around and around the sun. And they can cause the sun's brightness to go up and down. And I'd been studying this for 8 years. So I sent an email to this guy, Bill Borucki, and I said, you know, this technique that you're proposing sounds really great and all, but I'm very skeptical because of sunspots. And he said, great, that's what we need. He said the last proposal was rejected, and that was one of the reasons why, because people had that same skepticism. So the answer is that the transits, these dimmings of light that happen to planets, from planets, they happen on different timescales than the spots going in and out of view. There are also other kinds of astrophysical signals that can confound us. For example, you have binary stars, two stars that are gravitationally bound, and they can eclipse one another, and they can mimic planets. So we have to know that whole laundry list of things that can fool us, and we have to do the homework and the ancillary observations to cross them all off the list before we say it's a bona fide planet. And that's why of the 4,500 signals that Kepler detected, only about 2,500 have this confirmed status. The others haven't yet had all of those things scratched off. Yeah.
Me and my friend are really interested in this stuff. We have conversations in the car, we carpool, and we talk about
There is hope for humanity.
We talk about like astrophysics and like theories and philosophy all the time. Okay. And one of our biggest things is like light doesn't travel fast enough for us to see it. It travels fast, but it travels like light years. It takes light years for the light from planets to get to us. So out of those 2,500 planets that we saw, a lot of them have got to be pretty far away. So the chances of us seeing life on them is we won't see it for a long time because light doesn't get here fast enough for us to see it as it evolves.
Great point.
So what are the chances of us seeing life at all?
Yeah, very good point.
Right.
Well, how long has life been on planet Earth?
It's like 3 billion years or something like that?
The oldest fossils, yeah, over 3 billion years old. Humans have only been around for, let's say, 100,000 years or less. So not very long. But both of those numbers are pretty large, right?
Right.
So then you ask yourself, okay, well, how far away are these planets? And the most distant planets that Kepler found, well, most of them are like 3,000 light years away. So that's actually not that far, right? If it takes light 3,000 years to get here, but life could exist on the planet globally for 3 billion years, then I'd say we have a pretty good chance. And in fact, the kinds of planets that we will go searching for life on are all going to be within 100 light years.
Oh.
Those that we're going to look in the solar neighborhood
Okay.
to find life.
Cool.
Okay, we have time for last question.
How would you improve Kepler?
How would I improve Kepler? How would I improve Kepler? Such a great question. I would have improved it by putting more gyroscopes on it. Because we had 4 the gyroscopes control the pointing of the telescope, and we only need 3. And we had 4, but 2 of them broke. So we didn't have enough redundancy. That means that if one breaks, you swap in and put a different one. So I would have put in like 6. Because then we could have had Kepler running for like 10 years or more. And we could have stared at the same patch of sky in Cygnus the Swan. And if we had stared at the same patch of sky in Cygnus the Swan for 10 years, we would have found, I don't know, 100 potentially habitable Earth-sized planets. And I really, really wish we had been able to do that. Yeah.
Okay. On that note, let's thank Natalie for a wonderful talk.
Thank you.